Now that we have the general solution, we'll look at the time-ordered or the time-dependent eigenvalue in the separation of variables for Schrödinger's equation, which gives us I h bar t prime over t is equal to minus alpha squared. Alpha squared is, of course, some energy that would be denoted here. We've separated this. Each of the separated variables are functions of time only. Very straightforward. I h bar t prime equals minus alpha squared t. The function t, which is the function of time only. If you divide by I, it's the same as multiplying by negative I. So we would have t is equal to I alpha squared t all over h bar, which gives us the very simple solution. This is t prime, and we would have t is equal to the exponential of I alpha squared all over h bar times time. Now what we want to do is now find the boundary conditions. This really jumps out at us as de Mobray's equation, which would mean that this should be equal to 2 pi I, and if that was true, then this whole thing would equal 1. Time would equal 1, which is very nice, because if we take t, x, y, z, which is equal to psi, which cannot be equal to 0, so it has to be equal to some of the boundary conditions. But if it's 1, one of the nice properties of 1, if each of these are equal to 1 at the boundary conditions, we have the same boundary conditions for each for both time and for space. So this would basically mean we take this part here, which is I alpha squared t over h bar would equal 2 pi I. The i's cancel. We have alpha squared t is equal to 2 pi times h bar. That's equal to some energy, so we will denote that as the energy of the electron. The energy of the photon that's coming in times time is equal to basically h. And there's our boundary conditions, which would set time equal to 1. So we will just move this up here so that we see that Et equals h, which would be one of the, equal to Planck's constant, which would be one of the boundary conditions, or the time-oriented boundary condition, if you like, to Schrödinger's equation.